Hello world. Yeah, welcome to the presentation about deterministic browser. Sorry.
Yeah, so next up is Zhanhao Chen from Lehigh, and Zhanhao is actually finishing up his master's degree this year and will be on the job market. So once again, we have all good candidates during this session.
Thank you. So, welcome to the presentation about deterministic browser. And I am Zhanhao Chen from Lehigh University, and other co-author of the paper, including my advisor Yin Zhi and my co-workers Song and Shu Jiang. In this paper, we describe how we built the first deterministic browser to defend against a timing attack. My presentation mainly includes 5 parts. First, I will talk about our motivation, and then is our defenses, design, and implementation. And the fourth part is the evaluation, and the final part is our conclusion. Sorry. So I will first briefly talk about the timing attack in the motivation part. The general idea of timing attack is exposing victim's secret based on timing information. So what could be inferred for your browser? Here are 3 concrete examples. First of all, the attacker could sniff the browser history based on rejoin time. I will talk more detail about this attack later. And besides, an attacker can also infer the size of a file, such as your friend list on some social websites based on how long it takes to load that file. And also the attacker could infer the execution speed of your computer, which could reflect the computing power of your browser. That could be contribute to browser fingerprinting. Let's understand how the timing attack work with a concrete example. The sniffing browser history attack. Browser history is one of the most effective information to analyze users' behavior. Many websites are interested in it, especially some shopping website and video website, because they want to make some recommendation for the user. However, expose the browser history actually uh, violate the user's privacy, so we regard that as an attack here. From user's aspect, the user could directly know the browser history based on the color of a link. In most browsers, a visiting link is shown as purple, while an unvisited link is blue. However, this color difference is invisible to the web page, so the web page cannot directly infer the status of the link. So here is when the timing attack comes in. When a link is embedded to the browsers, it will always first show as a blue one, and then the browser will search its local database, and when the search result comes back, it will withdraw the link depending on whether the link has already been visited or not. So in Firefox, the browser will consume about 15 milliseconds to withdraw an unvisited link. For a visited link, because the browser need to change the color of the link, it will consume more time. In Firefox, it will take about 40 milliseconds. So the basic idea to infer the status of the link is to set a threshold to be 35 milliseconds. If the link takes a longer time to be withdrawn, then that will be a visited link. Otherwise, it will be an unvisited link. So the slide here shows the attack model of the sniffing browser history attack. In this case, the attacker will tie the rejoin event and also analyze it, so he can know that Google has already been visited while Facebook not. So after we analyze several timing attacks, we conclude that there are 3 necessary elements for timing attack: the adversary, the target secret, and the reference clock. In this case, the adversary is the JavaScript code. It will tie the rejoin event and analyze it. And the target secret is the rejoin type, which could be used to infer the status of the link. And the reference clock is used to obtain the timing information. In this case, is the real clock. So then I will talk 2 kinds of timing attack. The code in this slide is used to infer the execution speed of the user's computer. it could contribute to browser fingerprinting. The attacker will first obtain the start type through performance.now, which is a JavaScript API to obtain the current type. And then the attacker will assign a specific JavaScript job to the browsers. In this case, the adversary will run a for loop for 300 times. And after the job, the attacker will use performance.now again and calculate the duration of the for loop. So because all of the workload is running synchronously, so we call this kind of attack synchronous attack. On the other hand, for asynchronous attack, it usually make use of the callback mechanisms. This code is used to obtain the rejoin type in the sniffing browser history attack. The attacker will first use performance.now to obtain the start type, and then he will call the request animation frame function, which could involve the rejoin event. And in the callback function of the rejoin event, the attacker will use performance.now again and calculate the duration of the asynchronous job. So this slide shows the three necessary elements in both cases. Let's take a close look at these three necessary elements. The adversary is just looks like normal JavaScript code. If its responsible is to assign some job to the browser to expose the target secret as well as obtain the timing information. A target secret is what the attacker want to infer from your browser. In the synchronous attack, the target secret is the execution speed of JavaScript code, while in the asynchronous attack, the target secret is the duration of an asynchronous job. And a reference clock is used to obtain the timing information. In both cases, we use performance.now. Besides performance.now, there are many other asynchronous reference clock in your browser, such as post message and set timeout, which could be invoked repeatedly in a stable frequency. So after brief introduction to the attack, I will go to our story, how could we defend against a timing attack. In this session, I will first talk about our basic concept, the reference frame, and then I will talk the detail about the defenses against synchronous and asynchronous attack. So the one possible solutions to defense against timing attack is to remove one of the necessary elements out of the browser. However, we cannot directly remove one of them because they are related to essential function. So the first thing we do is we divide the browser into smaller units, which we call that reference frame or RF. This concept is borrowed from physics. In physics, RF has independent coordinates, including a time coordinate. So we define the RF here as a specific clock that tick based on certain criteria. You can also see that RF is naturally implemented as threads in operating system and browser. So after we split the browser into smaller units, you can see that the necessary elements will located in different RF. Some RF may have all of the necessary elements, while others have part of the necessary element. So our solution is to ensure that at most two necessary elements coexist in the same RF. Because the timing attack requires all of the three necessary elements to coexist in the same context. So in this way, we can defend against that. Okay, now I will come to the detail about our defenses strategy. First, I will talk about the defense against synchronous timing attack. Synchronous timing attack is running on JavaScript RF, which is also the main thread of our browser. So what we have done is we replace the original clock and replace it with a deterministic clock. A clock is deterministic because it will tick based on the adversary's input. So it will tick up for deterministic types for a specific JavaScript code. So let's take a close look at the adversary's input, which is the JavaScript code. JavaScript code will be first translated to operation code or OP code, and then it will be interpreted or transfer to machine code depending on the execution mode. So in this procedure, we could use the number of opcode to represent the adversary's input. So our new clock is just the opcode counter. And we also make sure that the clock will keep ticking when even there is no opcode running. So let's understand how it can work with the code. So our modification is located in the performance.now API. We directly return the opcode counter. So suppose there are 100 opcode before the synchronous attack. Then the first performance.now will always return 100 milliseconds. And then the attacker will assign a specific job to the browsers, which is the for loop. Let's assume this for loop will consume 300 opcode. And then when the second performance.now is invoked, the result will always be 400 milliseconds. So the duration will always be 300 milliseconds in all browsers, so that the attacker could not infer the execution speed. Now let's come to the asynchronous attack. To defend against the asynchronous attack, we have to make the RF communication deterministic. Because in this kind of attack, the adversary will obtain the necessary elements from other RF. So what we do is we synchronize the clock when the communication happens. So let's come back to the code again. Suppose there are 100 opcode before the attack. So the first performance.now will always return 100 milliseconds. And when the adversary wants to assign an asynchronous job, we will predict how long it takes to finish that asynchronous job. Suppose we predict the duration to be 60 milliseconds. So when the callback function of the asynchronous job is invoked, which means the asynchronous job has already been finished, the first thing we do is we set the current time to be 160 milliseconds. So the second performance.now will always get 160, and the duration will always be 60 milliseconds. So in this way, we defend against the asynchronous timing attack. And this slide shows some information about our implementation. In this project, we implement a prototype of deterministic browser called Deterforce based on Firefox 51. And we modify over 1,500 lines of code, and the modifications are located in 40 different files. And our modifications mainly including two core components. In the JavaScript engine, we place our deterministic clock there, and we also modify multiple RFs, including the timer flag and the script loader. We achieve the deterministic communication in these RFs. So next, I will talk about the evaluation for our prototype. In the paper, we describe 3 kinds of evaluation, including the robustness, the performance, and the capability of Deterforce. So the first evaluation is to test the robustness of several browsers against the timing attack. You can see in the tables, each column represents a browser. The first 2 columns represent 2 industrial browsers, which is Chrome and Firefox. And the third browser is Tor browser, which use the Tor, which introduce some noise to the original clock. And the fourth browser is FuzzyFox, which follow the concept of fuzzy tie to defend against timing attack. And this paper is published in Usenet Security 2017. And the final browser is our Deterforce. So we test several timing attacks in this browser. First, we test the clock edge attack. This attack is used to increase the resolution of browser's clock. As you can see in the table, only FuzzyFox and Deterforce can defend against the original version of clock edge, which means this attack can successfully increase the precision of the clock in other browsers. And we also made some modification to the original attack. We made the attack execute for a long time and obtain the timing information asynchronously. Then we show that FuzzyFox can cannot defend against this kind of attack. Then we tried two kinds of side channel attack on the browser. The figure here shows the performance of the side channel attack. This side channel attack is used to infer the size of a file in your computer based on the loading time. It will consume longer time to load a bigger file, so the attacker could infer the size. You can see only digital force can return the deterministic loading time for different file, and all the other browsers have an increasing curve in this figure, which means they are vulnerable to the attack. If you take a close look at the curve of fuzzy force, you can notice that it can defend against some of the side channel attack. For example, if the attacker want to differentiate a 1 MB file and 2 MB file, fuzzy force can return the same loading time. But after we increase the difference of file size, for example, a 5 MB file and a 15 MB file, then we can show that the side channel still exists in fuzzy force. And then we also tried the catch attack on this browser. Catch attack could be used to infer which website is running on other tab. So similar to the previous attack, Tor browser, fuzzy force, and detail force can defend against the original version, but we also modify that to make it run for a long time, then only detail force is robust to the attack. And the final attack is called SVG filtering, which is used to infer the content of a SVG image. It will infer the content based on how long it takes to process a specific image. Only detail force can return the same processing time for different image, which means it's robustness to this attack. So the table in this slide shows the performance of detail force and the Firefox to defend against the sniffing browser history attack. In Firefox, it will take about 37 milliseconds to withdraw a visited link, while it take 15 milliseconds to withdraw an unvisited link. And in detail force, the reported time of withdrawing event is always 60 milliseconds. So the second evaluation is to evaluate the performance overhead of our detail force. We first use a JavaScript benchmark called drawmel to test the performance. We compare the result with the same version of Firefox. We saw that detail force has 0.63% of median overhead and 1% maximum overhead. And besides that, we also try to load some popular websites on detail force. We load the Alexa's top 100 websites on the detail force, Firefox, Tor browser, and fuzzy force. You can see the curve of detail force is close to the legacy Firefox one. So the median overhead is 0.1%. And when you see the curve of Tor browser and fuzzy force, you can notice that it has a large overhead because they both introduce some noise to the original browser, which will cause some delay. And the final test is about the capability of detail force. We use a testing framework called Multi-Tech to test the capability. And this test framework will be tested on Firefox before every release. We show that the detail force can handle 97.6% of the tests, while the legacy Firefox can handle 97.8% of that. And we also try to use some behind login functionality on detail force. We log into Gmail and send email, receive email, and we purchase something on Amazon, and we watch some video, leave some comment on YouTube. And this function works fine on detail force, which means detail force can handle the popular website. So the final section is our conclusion. In this paper, we show that timing attacks still exist even with the previous defense, and we implement a prototype of deterministic browser called detail force. And our evaluation shows that detail force is robust to the existing timing attack with small overhead and is backward compatible to the real world website. So welcome to our website, detailforce.com. You can play with some timing attack in your computer there. And also you can see a video of the performance of Detail Force there. And our project is open sources. Welcome to check out our code on GitHub. Thank you very much. Any questions?
Hi, nice talk. I'm Tom van Goetem from the University of Leuven. I was wondering, in the asynchronous case, how do you know that one reference frame communicates with another one? How do you determine that?
So your question is how can we determine which reference frame is communicate with the current one? So actually we have to analyze all the timing attack and conclude that, for example, in the rejoin the sniffing browser history attack, we know that the communication is between the JavaScript RF and the draw and the request animation frame RF, so that we can make that deterministic. So if we want to make our detail force robust to all of the timing attack, we have to analyze all the timing attack and then modify the browsers based on that.
Okay. And a follow-up question: if there would be a covered channel between two reference frames, would Dieterfox still manage to defend against timing attacks?
Somewhat, sorry.
If there would be a covered channel, so if you didn't see the direct communication, but if the communication was through a covered channel.
So the communication between RF is achieved by the callback mechanism, so that we can always detect the communications inside the JavaScript RF. If you are interested in our detailed designs, welcome to check our papers. So it has more detail. Thank you.
Hi, Hovav Shaham from UCSD and UT Austin. We reached out to you with some flaws in your prototype implementation that you then patched with a pretty substantial patch to your system on GitHub. Are the overhead and compatibility numbers that you report from the version at paper submission time, or are they redone with the patched version based on our communication?
The performance report in the slide is based on the browsers when we submit the paper. Of course, we made some improvement to the browser now, so we haven't.
Do you believe that the version in GitHub now will have overhead as low as the one at paper
I don't
submission?
think so. I think the current version could have the similar performance as the version in this slide. Thank you.
Hi, Chris Kanish, University of Illinois, Chicago. So if I wanted to use like performancetimers.now and I wanted to make a similar defense where I just had it return 0 every single time, like there's no information whatsoever in there. What would your evaluation say about how fit that is for use on the regular web? Do you have any like random guess as to what would happen?
So if you directly return 0 in the performance store now, then some popular function will not work on the browser.
Like
so it will not compatible to the real world website. For example, if you watch a video that the clock will not tick in, and some JavaScript games they use the performance store now API, then you cannot play the game there.
Okay, so they're using it for a high resolution ticker for some reason. Because I guess my understanding of the reason that API exists is so that I can do exactly what the attack is. I want to figure out how fast does my page load. Like that's the reason. One of the major reasons that exists in the browser is to evaluate, if I do it this way, how fast is it? If I do it that way, how fast is it? Which one is going to be faster? That's why you want to have high resolution timers nominally. So I guess what I'm worried about is the functionality is probably going to break like this type of defense will break exactly that use case. And at that point, I wonder, like, why don't we just say, oh, you shouldn't necessarily be using that API in the first place on like commonly deployed sites?
I don't think the problem can be solved by simply decrease the resolution of the original clock, because we saw that falsifiers and Tor browsers, they do in this way. But if we made the attack execute for a long time, then the side channel still exists there. And why we want to check, want to make the performance store now keep ticking is we want to preserve the original version of function of the browser. And when there is no adversary or there is no optical running, then the performance store now will ticking based on the real clock, which is just looks like the original version of browser, which could preserve the original functionalities. While if there is an attack, an adversary, then we will replace the original clock to our deterministic clock.
Okay,
That's our
thanks.
design. Thank you.
Hey, Christian Steiko from TU Darmstadt. So I saw you hooked basically the Performance Now API to measure the timing attack, the time. But what about these network attacks where you request an image at the beginning of the processing and one at the end? And can your prototype deal with that, or is it hard to adapt to deal with that?
So when the attacker want to obtain the duration of an asynchronous attack, the only way he can do that is to use the callback mechanism. So so we modify the API of performance.now and as well as others APIs such as date.now. And if you take a close look at in our paper, we do a more complicated designs to defend against the asynchronous attack, such as the set timeout and post message. The paper describe how we defend against that kind of asynchronous clock. So if you are interested, you can see our paper. Thank you.